So one of the fundamental concepts in computer science has to do with a very old problem in game theory called the Byzantine generals problem. So let me sketch this problem. A general and his armies have laid siege to a city. The city's strong, but has resisted the attack. So the general and his officers have basically a decision to make. They either retreat or attack. And this is important. Both need to be coordinated. So if they all attack simultaneously, they will win. But if the attack is uncoordinated, then they will not win, they'll be defeated. So there are a number of potential problems that this mission has to deal with. So the general is communicating with officers through messengers. So there are many ways that this system can break down. So for example, the messengers might be traitors. The officers might be traitors, or the general himself might be a traitor. So let's kind of go through how this works when it works properly and when it doesn't work, when it breaks down. So here's an example. So the general gives the order to attack. That order is successfully transmitted to the officers. The messengers basically tell the truth. The officers are loyal. Everybody attacks, and they win. They defeat the siege city. There's another acceptable outcome, and that is the general decides to retreat. So again, the message is sent to the three officers. The messengers are loyal. The officers are loyal. They obey the order. Everybody retreats. So those are the good outcomes. Now, let's talk about the problematic outcomes. So number one is traitorous messengers. So the general sends a message to retreat, but two of the messengers change that message into attack. So officer one attacks, officer three attacks, but officer two, they retreat with the general. What happens is officer one, officer two, and their armies are defeated and die. So there's another version of this where the messengers are actually honest. So the general sends out the order to attack to all three officers. So it turns out that two of the officers are traitorous. So the general attacks, the officer number two attacks, but number one and number three, they don't attack. So it turns out that the general and the second officer, they're killed in the defeat, and the two traitorous officers survive. Okay, the third possibility here is the traitorous general. So the general sends out the order to attack. And you can imagine that it's possible that the traitorous general retreats. So the officers that actually obey the order and attack die. So these are the outcomes of this Byzantine general problem that basically caused this system to have a fault. Okay, so what we need to do is to design systems of blockchain consensus to avoid problems like this. So we need to deal with the possibility that some of the nodes on the network are not trustworthy. So we need to build Byzantine fault tolerance. We need systems that are tolerant to the same type of problems in the Byzantine generals problem. Okay, so this is designed so that we can implement a distributed system and not have a lot of trust in the system participants, so the different nodes. So the goal of what we're after is to build a consensus mechanism that's Byzantine fault tolerant. And it turns out the algorithms I've already talked about briefly, and we'll go into more detail in this module. Things like proof of work is Byzantine fault tolerant. So it is designed in a way that there are safeguards to avoid the same sort of fate of the Byzantine generals problem. So it turns out with blockchain technology, there is a spectrum of different possibilities here. So we'll see different methods of dealing with Byzantine fault tolerance, but even within these methods, there are different choices that can be made. So for example, it might be to be very, very secure, it means you need to trade off things like speed or security. So some of these implementations of consensus will be more resilient than others. And that is an important trade-off that is very specific to the application of the blockchain technology. So we need to apply a blockchain technology and a consensus mechanism that matches the particular application. So how much security do we need? How much speed do we actually need? These are all choices. And if we need security, it might be that we have to pay for it with a lack of speed. So these are trade-offs that are specific to particular applications.